Audio, share. Oh no, no, go away, go away, live somewhere else. There we go. We want this one. I want to go to the beginning. One of these days, I'm going to bring my, what is it called? Mouse and keyboard and just do it from over there where I can actually see. Okay, hopefully David can see everything and not just the title slides here. We were talking about Mars. We were talking about the Earth. We're going to talk about the similarities between Mars and the Earth, in particular in the context of water first. And in particular, we're going to avoid the atmospheric talk until we sort of go over what drives atmospheres, and then we'll do them all together. So let's cut up a little bit. We'll talk a little bit about the surface geology. We'll talk about the history of water on both these planets. And we were talking about how water was delivered, so we'll talk about what the history of observations of water on our planet looks like. Questions so far? Okay. You started the homework? Yeah. Oh.
Not the new.
Not the new one. Okay. But you're doing the old one?
I have most of it. I just need more words.
More words. Okay, good. All right. More words better. This is a face of an alien on Mars, right? Absolutely. Absolutely. Everyone agrees? Good. All right. So now that you've risen to the level of this class, you now get to learn that aliens exist. No, that's a lie. This is just one of the human beings' better attributes is the ability to see faces where there's not faces. Our brains are hardwired to look for faces. Anything that looks like it has eyes and a nose, we're like, okay, let's alien. Okay, but it's just rocks. Okay. These observations that I'm going to tell you about today, we're going to start with the Earth. And we're going to talk about the global temperature and how we know the global temperature to the level of accuracy that we know it for the last 100,000 years. 100,000 years, right? That's not like weather stations for 100,000 years. This is like understanding the geological record. We'll talk about Mars, and then we'll talk about the similarities and the differences. What's the major difference between Mars and the Earth? Sure, but what's the major difference? Big. Right? Biggest difference, and the easiest way to have a conversation with anyone when they talk about Mars, Mars small. Right? Mars small. Mars not habitable. Okay? Every conversation begins and ends there. So there's a lot of stuff about colonizing the solar system. One, talk about the ethics of colonization. We can do that if we want to. It's stupid. Okay? There's no reason to. We have a perfectly good planet. Some resources well here. But the second thing is if you choose Mars as a target, you can never fix the Mars small problem. So let's say you deliver it hundreds of millions of tons of atmosphere, it will disappear. Right? Okay. So let's use the one that has perfectly good atmosphere to the best of our ability. So speaking of that planet, that's okay. This is a slide that I like to show in my intro astro class, but apparently you guys didn't see it or didn't memorize it. So this one is the age of the oceanic lithosphere. So this doesn't tell you anything about the age of the plates, the continental parts, just the lithospheric part. So here's the Mid-Atlantic Ridge that I told you about. Brand new seafloor spreading. And you can, of course, see that these two are connected. Right? And we find fossils here and here of identical age and same animal. Right? I think recently they found foot tracks start in one of the plates and go to the other. Like continuous set of fossils. But like, oh shit, that's the same path, same animal was walking, right? So that's pretty cool. Do you guys know what the oldest piece of crust in this picture is? There you go, baby. Where is it? I know, but where in Australia? Isn't it? It's right, the type right butt fuck there. So in the middle of the Australian outback, you find the oldest pieces of rock. They're called zircons, and they're like 4.2 billion years old. Somehow they've survived. This is a piece of continental crust that's massively old, and there's very little erosion. It's been a desert for a millennia. Right? It's very convenient for us. Okay, and then you see these are seafloor pieces. Here's your Himalayas. All of the geography of the Earth can be understood in a diagram like this, right? You can immediately see the location of various plates, but you can also see where you might have subduction zones when we were talking about tectonics. So here, for example, that's the Andes. Why is the Andes so tall? Well, look at who's right next to it. You have this seafloor that's pressing the Nazca plate directly into the South American plate. One of them has to go up, one of them has to go down. So this one is going down into this ginormous trench. And of course, if you're a real nerd, you go to your local library where you can find a relief map of this. And they'll have the trench and you stick your little like 7-year-old finger in there and see how tall and how short these things are. They're exaggerated, obviously, but it's really fun. And so you can say, okay, why the Himalayas be like that? That's because India's got a real problem with the Eurasian plate. It's trying to fight. Okay. Cool. Okay. I also promised you some Venus stuff. I think the image that I was thinking about is a Mars success image. So we'll talk about that when we talk about Mars. You can't read this, and it's not because it's far away, it's because it's in Italian. So it says numero di missione, which I don't know if you know what that means. Oh, very good. Okay. And then this one over here, diametro. Good. All right. Is it Spanish or Italian? All right. This one is nazione o ente finanziatore. This is the nation of the mission origin. So as you go around here, you can see all the missions in order from the 1960s to the 2020s. And you can't read these in most cases, but some of them you can. That's Venera 5. But what this doesn't tell us, of course, is which ones are successful and which ones aren't. So you can see that the USSR, which is colored red here, sent 32 missions. The United States sent 10, and Europeans sent 2, I believe. And the Japanese sent Atatsuki, which is just the 1. But if you combine this information with one of these, you can kind of see how frequently we visited. And thankfully, the colors here pretty similar, right? So very successful. Thank you, whoever created this one. This is oriented by the types of things that they studied, but you see the same thing a couple different times. So there's multiple Veneras. This is like Venera a number, and this is a different Venera. This is the Venera class of missions. And so Venera 14, somewhere in there, right? And we'll see Venera 14 within 2 seconds. And then the Vega missions as well. Galileo was a probe, descended into the atmosphere, burned up obviously at some point. Cassini did a couple flybys in order to get the energy necessary to go out to its final resting place, which was Saturn. Messenger did a couple flybys on its way to Mercury, and Venus Express was in orbit. I think it's still in orbit. We forget. And then FX2P is not on this one, obviously. So we had the Mariner missions up here, Magellan here, etc. Okay, so you wanted pictures of the surface. What does it look like, Krismani? So what do we expect it to look like?
Surface of Venus?
Mm-hmm. Very good. Okay, everyone got that right.
Down at
And do you know if that Suki is still there? No, right? It's ATASUKI. Yes, I might have spelled it.
Looks like it's still like.
Awesome. Okay. What's the surface look like? Rocky, good. Basaltic, why basaltic? What does basalt mean again? Right. So we have an expectation that a lot of the surface should be volcanic. What's the age of the surface again? New. It's between 6 and 7, depending on who you argue with, right? So 600 million years old. We think the entire surface was catastrophically reformed. So the expectation is that if it's molten magma, it should look very similar to the lunar mare, at least at first glance, right? Because what is the mare? Mare is a volcanic, right? You puncture the surface. Sorry, you don't puncture it. You weaken the surface, and lava seeps through the cracks and fills the entire crater bed. It's very different than the smaller craters, right? You punch in, right? You can, for example, redistribute that material. You can melt it. You can create this perfect little cup. But you don't puncture, I keep saying the word puncture, I shouldn't say that. You don't weaken the crust enough that it provides a source of volcanism. The mare is different, right? Because you weaken the crust enough, there is magma so close that it can just make its way through and flood. Okay, so the expectation should be that it's basaltic, and we associate basaltic with the color. Good. Anything else we should expect to see in this image that I'm about to show you? Smooth. Okay. Anything else? You expect erosion. Okay.
I'm not arguing against it, but
Okay, good. All right. Oh, shit. Well, it looks better in my computer, but you can look at these later when I post the slides. Oh, why did that show up again? That's weird. Okay, these are the Venera 14 images. There's a couple of them that made it back. What? Yeah, pretty yellow, right? No one said that. Now, this is the atmosphere. The sulfuric haze atmosphere. It's real fucked. Not good to breathe. We're going to talk about the atmosphere much later, obviously, but it's melting and poisonous and 90 times greater than the pressure that we would feel now. So, for example, one of the easiest ways I like to think about this, anyone here ever go like swimming, like snorkeling, deep sea snorkeling? So you go snorkeling and you go down, and every 10 feet or so, you have to like clear your ears. You ever notice that? About 10 to 15 feet, you gain about 1 atmosphere. It's clear your ears. This is about 90 atmospheres. So this would be like diving to 400, 500 feet, depending on how you. Yeah, right? Okay. So this is like standing on the surface. I'm gonna obviously it's not gonna feel like air, and it's gonna be hot. It's gonna be the worst hot you've ever hotted. And the surface itself, you said black. I think this is black. But you said smooth. Doesn't quite look smooth to me. Why? Okay, so we don't know anything about the atmosphere yet. We don't know if there's surface winds or anything like that. We do know there's certainly no water, right? So the absence of water means there's no surface like rivers or streams or anything breaking it up. So this could potentially be from wind, but notice how these are fractured. This is from cooling. So you might have started with a completely hot magma, and everything is nice and the same. And then as it cools, it cracks. And afterwards, you have tectonics, right? So we probably are not seeing evidence of erosion in an image like this, but instead you're seeing the effects of chemical weathering due to the fact that it is obnoxiously hot, right? And you have the atmosphere interacting with the top of the rocks, but also as the ground moves due to tectonics, right? So even if we don't know if volcanism is occurring today on Venus, we definitely know that there is motion due to the fact that the inside is still magma, right? So we talked about tectonics being the crust pulled and pressed by magma underneath moving around, right? So for example, we go back to this image. Okay, we want to understand what's happening here. This is spreading, and that's because magma is coming up hot and pressing the crust apart before it sinks, right? Twice sinking below these objects. So you can imagine if I were to do a. All right, David, this is a picture. I'll send you a picture maybe. I didn't plan to do this. Okay, so here is your crust. Okay, idealized, right? Here is your the boundary between the Nazca plate, right? And then here's your trench for the South American plate. Okay, and then way. Here is your mid-Atlantic ridge. So let's map the magma. Where is it coming up? The first approximate. When you say through, what do you mean? Right, remember that it's not just like, it's not like I say something. Not like a hole. Right? So it grows, I think, something like a centimeter per year, something like that, something really small. Yeah, this is as if I cut it this way. Now I'm looking, this is down deep into the surface. Down into planet. So let's do this part here. Let's do hot 4. Okay.
Left to the.
So let's do this one first. Is magma rising or falling? Rising. Okay. And then it reaches the surface and it's forced to turn. So it takes one of 2 paths. Right? We saw this diagram. Okay, as it moves, it seeps out. A little bit of loss. Now, generally speaking, these are convective cells. They are rotating a bit. Right? And really, this is not like it's going right to the surface. There's this whole section here, which is solid. It's just that as it pulls apart, it's weak. And just like we saw on the moon, it seeps through. Right? So it's not like liquid here. It's solid. Okay. So this pulls apart and it's fluid. So what goes up has to go down. Let's go over here. Let's go to the Nazca plate. This is also a place of spreading. So which direction is it going? Up. Right? And then, right, same logic. And now, you have a problem, right? They're going to meet, right? Yeah, so the question is where? Because remember, this one is being subducted, and this one is being pressed up. So somewhere in the middle, you have stuff goes down. Make sense? Right, because this is going to travel underneath the South American plate. It's going to run into its friend and sink. Make sense? Okay. Cartoon image. This is much more complex. This happens in 3D. This is an idea of how seafloor spreading works. Right? Okay. Not this. Okay. All right. Good. Where were we? All right, Ed. Okay. How do we take these photos? Well, oh fuck. How do we take these photos? Well, we send a cool color strip. Has RGB on it. And you just take a picture in the lab at home. And then you take the same picture on Venus. And you're like, wow, this looks fucked. But at least if we can correct for these colors, then it'll show it to what it would see for our. Right?
I would think it would be
What?
I would think it would be really too, almost too bright.
Why right? Yeah, so one thing that is a little tricky here, right? We haven't talked about the atmosphere as a whole, right? So you don't know how it's all distributed. But one thing is if you look at this image. Come on. You see this? What? Yeah, there's like something in the mount in the background, right? Do you see anything else? No. So on a clear day here, how far can you see?
Or, you're on the hill, like-
Oh, if you're on a hill, yeah, we're not on a hill. Okay. Straight line. Okay. So if that were true, I don't know if those numbers are right. If that were true, you would expect to see something, right? Is Venus super flat? No. But even stuff that's nearby, right? It's really hard to see. Atmosphere is so thick and there's so much gravity. So one thing that you're gonna remember from Venus is that the albedo is
Very low.
high. Very high. Yeah, the surface, you're right, very reflective, very not reflective. The top of the atmosphere, when you see it, just like that was a picture, it's very beautiful, right? Because it reflects so much light. Remember? What was the number? Yeah, it's like 67. Yeah, something like that, about 2/3. So 2/3 of the light gets reflected. Uh-oh. If 2/3 of the lights get reflected, what happens to the rest of the light? It travels down into the atmosphere. So even though you're closer than the Earth, if the Earth has an albedo, say of 30%, so only 30% of the light gets reflected, you can do a back of the envelope calculation to see how much light in each case you're getting, right? And that's even before you begin to bring in the fact that there's so much scattering. So it won't be super bright there like it would be at, say, Mercury. Mercury, you look up and it's the fucking sun, right? This one is going to look like, what's that film? Blade Runner, right? Where everything is very yellow and it's very hazy looking and it looks kind of darkish. And that's because you're sitting under almost 100 kilometers of cloud.
So it's not 30%, probably.
Yeah, we'll talk about the energy budget a little bit later, but yeah, it's a little bit more than that. Okay, cool. Oh God. All right, enough. Come on now. God. Why is this never? There we go. All right, let's talk about Earth. Earth has surface water. Yay! We drink surface water. Right? None of feel weird about that. Drink surface water right now. Please fight. So we think that most of what was brought here by meteorites, either in the context of the far asteroid belts, right? Probably some comets, but it had to cool off enough that the atmosphere was lower than the boiling point at 1 atmosphere. This has some caveats to it, right? Because if there was atmospheric loss, of course, you could potentially think about, let's say we start with more than 1 Earth atmosphere. Say we start with 1.5. And over the course of 4.5 billion years, you lose half of an atmosphere. Right? That would be a way of talking about, okay, maybe you could keep water there for longer at a higher temperature. So there's a fun game you can play. If you increase the pressure, then it stays in a liquid form at higher pressures, right? You've seen this? And if I lower the pressure, it starts to boil, right? Spontaneous. Okay. So, we talked about that last time. Inner solar system planetesimal, probably the outer main belt, and we'll talk about that distinction a little later in the semester. And about 10% of it is coming from comets. You can tell this because of deuterium abundance. So we're going to talk about this. You know, we did rubidium strontium, and that's a really fun one if you're a rock person. Not. So I'm an atmosphere person, and this is one of the most important atmospheric isotope ratios, and that is the D to H ratio, as we'll talk about today. Okay. So where's the water? On the surface, good. Where on the surface? How much is in the ocean? Very good. We're good at reading. Did we know that already?
I know it's a lot.
What?
I know it's a lot, yeah.
You knew it was a lot. Did you know 97% of it is in the ocean? How much do we drink? 3%. Do we drink 3%? Or is that all that we could drink?
Oh,
So we could drink, right? Okay. So 2% of it's in the ice caps. Do we drink the ice caps? No, in fact, that water never makes it back to us. So in fact, what we drink is actually way less than 3%, and it's way less than 1%. Because we are nothing, and the earth is big, right? I know, it's quite impressive. So think about all of the water you've ever drunk in your whole life. What?
That's a scary thought.
It's a scary thought.
Yeah.
Yeah, it's a low percentage. Well, and the crazy part too is we'll talk a little bit about climate change when we talk about the atmosphere as a whole. And there's obviously a hydrological cycle when we talk about atmospheres in general. But you know, everything that you've ever peed has then gone into streams and rivers, and that goes out to the ocean and gets recycled. So you know, your 1% or less than 1% is not the same 1%. We're not drinking from a exhausted supply, so that we have a nice balance, and there's obviously some purification. Okay. So keep in mind, by the way, astronauts directly drink their own pee, so it's better than that. Right? Do you understand that? Okay. Good then. Yeah. I'm not saying they drink their own pee for fun. I'm saying it's totally. Yeah. So it's not reintroducing a hydrological cycle. Okay. So geologists call this time the. Yeah, good. This lasts 2 million years. Okay. I'm sure there's a good reason for it. I don't know. It's all of these different, you know, the KPG boundary, the Cretaceous, what was it, K, right? What?
It's a C, but they use K for some reason.
Yeah, and then the PG, anyway. It's something, yeah. So as you look back, right, you look at geography and geology, right? And so you start now, and then you look backwards, because we know that it had to be layered, and you go through and you start labeling things by different names, right? And of course, the KPG boundary is that location where there's iridium found in multiple locations on the entire globe, which was only due to impact craters we talked about before. So you can have different demarcations in the availability or the abundance of certain things, right? So in the last 2 million years, water has fluctuated wildly in ice by a factor of 2 or 3. So what that means is that, you know, let's see, let's go back one more one. So I said that fresh water, for example, is mostly in the ice caps of Antarctica, let's say about 2%. That number can go up a lot, like to 6% by a factor of 3, or down, like 1%, right? What is that telling you as a planetary scientist? If I tell you that the ice caps shrink and grow. Cold, hot, very good. As easy as we can think about this is the way that we want to think about this. When the caps are 6%, that means cold, right? So when the caps are 1%, that means hot. Good. Now we'll learn. Okay. All right. All right. So We also notice that there's average annual temperature fluctuations of about +3 ±3 C. Some of the places that we see evidence for these ice changes is in glaciation, right? So you have evidence of glacial action requiring large ice caps in both hemispheres. So if you've ever thought about, for example, Yosemite, which is where? But where? What state?
California.
California, good, okay. Have you ever had a glacier in California? You've been through a glacier in California?
I've been there, but.
They have been. If they are right now, that would be kind of surprising, right? Right, they'd have to be very high up to survive. And most of California doesn't have any permanent snow cap, right? So glacier is not going to do super well. But if you look all over California, you see evidence of ancient glaciation. So how is that possible, right? Now, of course, you can run all these things back in the last 2 million years, and the plates don't really move that much. So it's not like California was recently as high as Alaska, right? So something had to have changed. There had to be ancient glaciers that carved through these objects, right? Okay. You can also see the place you live now. This is this is not from anything you know. These are Great Lakes, Finger Lakes. This is all from Rochester, in New York. So you can measure the ocean temperatures throughout the ages by looking at the heavy oxygen and the hydrogen relative abundances. So for example, H, you can just add an extra one. Has no problem having an extra neutron. So H with a proton and a neutron is called heavy water, or 2 hydrogen, not H2, but 2 hydrogen. And we're going to use a symbol D for that. It's called deuterium. But similarly here, you have your normal oxygen 16, and you just add a couple of neutrons just for shits, you know. You can also add, oxygen 17. It's like, yeah, whatever it is, throw in some neutrons. And the fun thing is, of course, is that these are very volatile. And what I mean by that is they like to be incorporated into water. So if, for example, you think about water as a rock, just for one moment, we're going to make an analogy, okay? You have it in the liquid stage, it condenses into something hard. When it does that, it freezes into place these abundances, just like the strontium-rubidium ratios that we saw before. When they were melted, you had a nice mixing pot of whatever the initial abundances are, you freeze it, and now it holds on to that, and then of course, some of them decay. 18, 16, they're not going to decay, but they will tell you about those original abundances, right? So if I go and I measure it, this tells me what the abundance of these were in the melting pot in which it came from, right? And this is like a biomarker, I should say. This is a marker for activity. Because if you have a reservoir in which one type of hydrogen is more abundant than another, then you can say if this water is more similar to this water, right? And I'll talk about some of the fractionation processes when we talk about atmospheres. Okay, so in general, we're going to talk about ice core samples in the seabed and in the ice caps. This is where you're going to get a lot of your DH for a really long time. Has there anyone ever seen an ice core? You know how they're made? Yeah. Oh, that's the next one. All right, next one I'll show you an example. You just cut a hole in the ground, and the ground should be ice. And then you grab the ice, and it's got to stay cold, so that you can compare like little samples through time. And just like when we think about sedimentation on the seafloor, which is preserving records of everything that happened. So let's say you go to a place that's pretty cold pretty often, and let's say there's no chance of it ever melting, then you can be confident that all the snow that fell on top of it is going to become compactified and become icy, and it will preserve both the composition of the ice and any air that gets trapped in the bubbles before the ice forms. Right? Have you ever had a piece of ice and you look at it and it's not perfectly clear? You know why that is? What?
Bubbles.
Trapped gas, yeah. There's tiny, tiny bubbles, right? I'm done, but I was gonna pull an ice cube out, you know? So, it'd be, I guess, rose color, coffee, but. But if you go and you think about like, how do you get clear ice, that's ice no imperfection. And of course, in general, that's not what ice core is, you want those imperfections. You can see both the ancient atmosphere, ancient older atmosphere, and the composition of ice itself. Okay. So, you may recall that there's this thing called vapor pressure. What that is? We're all reading the book, right? We're learning up good some compositional arguments about chemistry. Okay. So vapor pressure talks about the ability for something to be in the vapor phase as opposed to either a liquid or a solid, right? And there are differences in the isotopal logs of water. So what I mean by that is, let's just imagine the simplest scenario. You have a substrate, we'll assume that it's the desk. Okay? You embed in the desk different types of water. You put H2O 16. You put H2O 17. You put H2O 18. Which of those is the heaviest? 18. Good. All right. Now you put HDO 16. And you put HDO 17. And you put HDO 18. Which one of those is the heaviest? Right. Okay, so you're noticing a trend. You're increasing the weight. Now provide energy to the substrate. Okay, think about starting from below freezing. As you raise that temperature, which is the first to leave the substrate? Just like if I was a hydrogen alone, right? The thing that I can give kinetic energy, because remember, the way that we're thinking about gases, for example, is that in the gas form, they are individual billiard balls bouncing off of each other. And the heavier billiard balls do more damage, they give more energy than the smaller billiard balls. So if you have a giant one that's 20 times larger than the other, then the 20 times larger than the other hitting a piece of hydrogen will make hydrogen go flying. Right? Okay. So there are significant mass differences in how things vaporize. And similarly, the opposite's true. Let's say it starts to get cold and you have all of them mixed in the atmosphere. Who falls out first? Right? As it gets cold, you have sedimentation. Right? Okay, so this is called mass fractionation. You get fractions of mass dependent species. Okay.
This is how you measure them, you just measure the ratios of the heaviest stuff to the lightest stuff, and that varies over time.
Yeah, and we'll see this in an isobar in better. But here's the calculation, right? So here's your H216O, right? HDO, H218O, H217O, etc. There isn't really a D16O, but I just need to say that for okay. Because this one here, sorry, this one here and this one here have the same weight. Okay. But there's other chemical differences that we care about. So the easiest one to measure is the D to H, and that's just from this ratio. And HDO is rare. It's not zero, but it's rare. And H2O is abundant, particularly in this form. This is what you're drinking now, or at least I was drinking on it. Okay. So compared to normal water at a lower vapor pressure at every T, it's quite sensitive to T, right? Okay. You like think about icy water, you get more thirsty. Okay, so less D to H in an ice cap or a plant means there must be more D to H in the ocean water. Okay, and we think of that as the lower temperature of the ocean. So what did I mean by that?
There's more D to H in water. That means the ice cap is bigger. It's freezing all the ice.
Yeah, so let's remember, let's break this down, right? There's two things happening. Right? So at a given temperature, which of these, let's say I start at the temperature of 100, and that's, imagine the number. Okay, as the temperature goes down, which freezes out first? Well, look at both. D or H freezes out first? D. D freezes out first because it's heavy. Okay, so if D freezes out first, then what happens to the D to H ratio? This goes down, so the whole ratio goes down, right? Good. So let's look over here. The D to H in ice caps or plants being smaller means there's more in the water. Does that make sense? Should they match each other, or is there an interaction? But when I look at the ice caps, right, these are the historical record. I can't really do this, but I have to understand the connection. So this is the hydrological cycle. They are connected, right? What is the process by which I get new ice in Antarctica? Freezing. What's freezing? Ocean water that evaporates, makes it to Antarctica, and precipitates. Now it's rare, right? We talked about the fact that Antarctica is the biggest desert, but it happens, right? There's obviously ice there, and it came from sunlight. So while the total abundance of water is quite small, you just wait a long time and you get a lot. Okay. So if you get your D to H from precipitation, then it remembers where it came from. Right? So if I have less D to H for a little bit of time compared to other time periods, okay, then I'm thinking, well, this means more D to H in the water, which must be due to lower temperatures of the ocean, which is the source for the D to H, right? When the oceans are hotter, right, what happens to the abundance in the ocean?
No. The H is evaporating off.
The H is evaporating really quickly, okay? The D stays. So this thing, but I mean, it's not by a lot, but it goes down, right? And the D's heavy. So that thing rockets up. Sorry, that thing rockets down. The ratios are bad for me. Okay, and then this thing goes up, right? Let me show you how. This is a fractionation process. So you have to keep track of both of them, and you have to think about how they both condense and evaporate. Okay. So negative values here of this D to H ratio. This is just how we define it. Standard mean ocean water is your Vienna water. It's like abundance of this reference factor. You have to have a reference to something. The Viennese did it first, I guess. So, all right. So here's how it works. Oh, this is coming out really well. These are dendrochronology measurements of T as a inferred from the excuse me as inferred from the delta D. So the delta D is the deviation from standard mean ocean water, and these measurements of delta D in the ice caps let us infer mean ocean temperatures, because we think we understand the connection. Okay, and of course that's all subject to, let's say you want to go and be a glaciology researcher and you want to work in climate over long time periods, you can go in and try and prove, oh, that convention that we've understood is not well known, but it is. Okay, so let's think about tree rings, right? Delta D and thus T can be measured as individual tree rings. So we can see every year in an ice core when it lands is basically different, right? How much water did I get in that year? And compositionally, it changes year by year, right? So this is how you get temperature as a function of T for the last few thousand years, right? So here is the current temperature. Oh shit, that came really long. Okay, that's this is deviations from the mean, right? You gotta set that somewhere. Go ahead and ignore that. This is like some normal fluctuations, right? So here's the year 1800, and what's happening in the year 1800? No.
Like that.
Oh no, not yet. That's way in the past. 1800 is
That was nice.
no 1800.
Was there nice?
There was an ice age. We're not getting there yet. 1800 is 30 years after this country was made. Okay. So you're like very recent, right? Boston Tea Party is 1770, 1760 something, right? Okay, that's right here. Okay? And these are it's lower than this period here in the 1500s. Lower than theirs. Okay, not so bad. You go back 1,000 years, you have some global fluctuation. You don't have something here that's like freezing everyone out. These are global, right? Not local. And then this is recent. So what happened right here? The 1900s. Industrialization, right? Real fun. Okay, and then this is the ice core I promised you. Again, it looks better on a computer. But if you just type in the word ice core, it's pretty sick. This is the piece of ice. They go in with a big ice core, which are really cool because the coring process itself has to stay temperature like above freezing. Below freezing. So you can't melt it as you do it. So you got to core it really clever ways and then pull it out. And these things go down far, right? Thankfully, there's not a lot of precipitation. So each one of these layers is not like a foot thick. That's like 1 year contribution. It's like thin, right? But you have plenty to work with. And you can do cores all over the place. Okay. You can see the different purities of the ice deposited in summer or winter. Talk about how that ice purity changes as a function of season. When we talk about ends. There we go. Okay, so here's your D to H. And this is temperatures for the past 420,000 years. In a 3.4 kilometer core sample. Is that big? That's a long core sample. Think they pulled it out all at once? No. So you dive, you drill in, and then you pull it out. Right? And you have core samples that you go and freeze. Thankfully, it's freezing when you do it. Right? So you just leave it outside, but you try not to put it in the sun so it doesn't degrade. Right? And here's the depth. Right? Here's the current D to H up here. And you can tell in here, there's all of these changes. Right? Like at this depth of 1800, it's quite comparable in some cases to what we have going on today. But sometimes it's real low. And what the fuck did we say about delta D? What does it mean again? Lower delta T is lower ocean temperature. Okay. Lower ocean temperature means higher D to H in the oceans, right? And lower D to H in the ice caps. You need to precipitate that stuff and send it to Iceland, to Antarctica, to make ice, right? Okay. So we're gonna interpret this delta D, we're gonna turn it into the word temperature, right? And here's temperature differences from present. Now we're looking on the right scale. So here's us, right? And this is now years before present, here's 420. Okay? So at the very beginning, it's near zero. Because deviation from present should be close to zero. And if I go back, say 10,000 years, what do I see happen? Drop in global temperature, and that's called a. Come on, folks, you said it before. Ice Age. Yeah. Like this award-winning film series, right? Okay, so that's your first ice age, 10,000 years ago. Now, global is quite different, right, than we've had many ice ages. So we're talking about in the 1800s. That's not quite right. I think it's 1100s when you had one in Europe. That's like real bad for everyone. Okay. So that's cold. Yeah, -8 is not good. Okay. But that's not so bad. You know, over here it's hotter. By the way, how old are humans? Let me rephrase this. Anatomically modern human. Yeah. No, that's right. So it's 200,000, right? Okay. So that's like here. Right? And then ones that we think have the same cognitive properties as us. Yeah, it's like it's out here. So we've been walking around for a long time. You know? We don't know how long we can communicate for, but some folks put it about here at 16. Our ability to survive is kind of strange. We see, of course. Now, I'm going to go on a tangent here, but you can track human beings as they move from place to place, just through their genealogy, and of course, archaeological records. And so you can correlate this with some of this stuff, right? Okay. This time period here, 10,000 years ago, it correlates really well with when we think people made it to the states of America, but there are people who argue against this for a number of reasons. So that was one of them, global ice age. What about this one? Another global ice age. What's this one? What about this one? Okay, interesting. So there's some patterns there, right? Oh. Okay, so those are all ice ages, and they're sort of interspersed with warm. So what's the normal condition for the planet? Colder than now, right? We're living in this like beautiful little warm time period. But yeah, you just wait a good 10, 30,000 years and it'll be cold again. Okay. All right, let's look at Singapore. Oh fuck, that went too far. God damn it. All right, there we go. So many folks have looked for periods of like periodicity. Right, so trying to predict when's the next ice age going to hit us, and when should I start building a bunker. And interestingly enough, you can find really weird stuff. So they find through Fourier analysis that okay, so you take this deuterated signal, okay, and this is what happens when you let a bunch of physicists play with data. Okay, so you look at this, okay, see this DH, And you say, huh, that's a really funny signal. I wonder if there is any oscillation. Up, down, up, down, up, down. Because you know that you can build very complex functions with Fourier analysis, right? Where you say, well, there's a mean mode that's at 2,000 and overlaid on that is a 20,000 and overlaid on that is a 400,000, right? And that gives you a much more complex shape, right? You remember from Fourier analysis. So here it already looks like there's some peaks and some troughs. So people were like, huh, I wonder if there is any Fourier analysis in that. And here's what it looks like. Okay. You see this? These are the basically power modes. So this is all periods of oscillation in terms of thousands of years. And look at this peak at 40. Right? Strong peak at 40,000 years. Oh, sorry, 40,000. Right? That might be wrong. 23. Should be one more zero. Yeah, that should be one more zero. So it's 23,000 years, 40,000 years, and 100. And this is zero there too. Here's the peak at 100. It's big. Here's the peak at 40, and here's the peak at 23. You see that? And I don't know how to spell 23. Well, there's line. Comma. Okay. That's kind of weird, right? So this is why we talk about ice ages when we talk about planetary astronomy. Because this is going to feed into a really interesting thing called not speak today. Milankovitch cycles. Okay. So these are 1920s. These are periodic changes in the orientation of the Earth. So if you have ever taken an astronomy class with me before, you'll know that the North Star has not always been the North Star. And even as recently as 12,000 years ago, the orientation of the pole was in a different location in the night sky, right? So the axis, right, let's imagine that this is the North Pole. And just like this is rotating, so this is us rotating throughout the course of the, just normal day, and it goes around, and it's pointing to the same part of the sky, right? Let's say over there. But over the course of 22,000 years, the location of that rotates once over 20. I almost just laser myself in the eyeball. Over the course of the 22,000 years, that whole thing rotates once, right? So that's axis precession. Okay, now there's something called nutation. That's not like cool mutants, from X-Men. That is the process of moving back and forth. Okay, so nutation means that the tilt becomes smaller, more upright, and larger. Now, do you remember what our current tilt is? 23.5, yeah. So we're sort of towards the more extended part, right? We're not so up, kind of more over. And that has a period of 41,000 years. Huh. That's interesting. And similarly, the eccentricity of the Earth's orbit, which is changing due to the fact that Jupiter is just quite rude over long time scales, just deforming our orbital semi-major properties, right? So whether that is eccentricity or how close you get to the sun, that changes on a period of around 100,000 and 400,000 years. Right? Okay. So some folks think that these orbital fluctuations are the origins of ice ages. Makes sense. Data seems to support it. This is not quite data, but you know what I mean. Let's see. Is this an animation? I don't know if that works. I don't think that works.
So would the ice age be 1 degrees?
Sorry,
Rotation?
What?
For mutation, would an ice age be like when we're closer to 21.5 degrees?
Very good question. Here's why they don't explain the ice ages. I'm just saying, right, it looks good, right? It looks really good. It looks like it, all the time periods into the power series Fourier analysis, right? Okay. So here's why they don't explain the ice ages. The variation in solar illumination is tiny compared to the temperature variation from other cycles like the solar cycle. Okay, what's the solar cycle? Does anyone remember? You ever talked about this? So the sun changes its activity, not how bright it gets, but how many geomagnetic storms occur. So it goes through periods of low and high activity, and that periodicity is about 11 years. And the effects of solar storms have been shown to be quite significant in heating in the top of the atmosphere. Heating in the top of the atmosphere affects the atmosphere as a whole, affects the temperature, right? Okay. So that's a giant source of energy that's not shown. There's no 11-year cycle there. And more importantly, the ocean current configuration is a way of redistributing energy on the Earth. Okay, so let's say I do, in fact, tilt it from this to this. I go from 24 to 20. Let's be generous. Okay, what does that effect have? If I go from 24 to 20, that means, let's say I had 0. Do I expect to have seasons? No, no seasons. Let's say I do 45. Strong seasons, right? Big swings throughout the course of the year, pointing towards, pointing away, pointing towards, pointing away. Huge swings. So if I move towards 20, you would expect the seasons to become more gentle. But the ocean, which is a giant body of redistributing energy, is going to change as well, right? Ocean really good at keeping heat. Ocean really good at redistributing energy. Good. Okay. And interestingly enough, the 2300-year precession should have opposite effects in the northern and southern hemisphere. But we get a global ice age. Right? So let's say I'm pointing like this, and then I'm pointing like that, and I'm pointing like this over a course of 23,000 years. Right? That wouldn't affect. That's a very northern hemispheric thing to think about, not the fact that the entire ocean changes temperature. Okay. And the eccentricity oscillation is the smallest, and the 400,000-year oscillation is the largest. But if you look in the data, the 100,000-year oscillation is the largest, and there is actually no seen 400,000-year oscillation. So it's just weird. Argue with a brick wall. There are people who love this theory and who use it, and there's some people who want to explain certain things about Mars using something called spin-orbit coupling. I don't subscribe to that. You want to go ahead and prove me wrong in 20 years? You're more than welcome to. Okay? That's the point of doing science. That people like me get to be wrong, and then you get to be right. If my students ever surpass me, I haven't done a good job. Right? Okay. There's a lot of weird coincidences. Numbers are weird. The way that we interpret them are weird. Let's look at some other ones. Here's Mars. You love Mars? Mars fun. Okay, everyone's favorite planet is Mars over here, right? Good. All right, A for Isabel. All right, so over here you have the mass. How big is Mars? Small. Tiny boy. Okay, so it's about 1/10 of the Earth mass, but about half the radius. Okay, average density. Yeah, but what do we call that? What is this? What do we compare this to? Rock, kind of rockish. It's not Mercury, right? Mercury was like 5. Yeah, so this is more like. Yeah. Okay. Cool. This one. Oh, what does that mean? Very good. And what is uniform density? Yes, yeah. But what do you remember the number? 0.4. So slightly more differentiated than uniform density. Now, of course, we do that, know that it's differentiated, we'll talk about that in a little. Okay, albedo. Oh, kind of surprisingly low, right? That's because there's like low albedo terrain all over the place. There's not like beautiful clouds and, reflective, there's a little bit of an ice cap in here, but it's not these giant icy areas, right? Okay. Temperature. Cold. Effective temperature, what does that mean? Right, so no greenhouse effect, right? Okay, then liquid water exists at that temperature. Good. Okay. Okay. Is that a major axis? It is farther than us. It is not hot, okay, even though it looks red and like a desert, it's cold. It's Antarctica-like, not Utah-like. Okay? Orbital eccentricity, big, chonkin, right? Now, here's the similarity part. What is that? Tilted, right? Its orbital obliquity is 25.19, and ours is 23.5. Oh, right? Okay, let's try one more thing. What's down here? The day is 24 hours? Oh, is it the same planet? Is that too weird? That's crazy, right? That can only be because aliens made it like that, right? That's evidence. Ancient aliens must have created the Mars, right? Okay, what's the year like? About 2 billion. Okay, so this is coincidence? Yes. Just like those other coincidences I just showed you 2 seconds ago. And I was like, numbers are fucking weird sometimes. Don't spend too much time thinking about them, okay? All right, let's look a little bit more in detail here. Oh, fuck that, I'm not gonna read that. Well, I guess you can see that later. So there's a cool cyclone on Mars, but I'll show you better ones when we do the atmosphere. Okay, there's Mars's moons. So this is Mars. Right? Deimos, Phobos. Okay. Japanese are gonna send a mission there. We're gonna land on Phobos with a rover, drive it around. We're gonna pick up some stuff. We're gonna bring it back. Gonna figure out what Phobos is made of. So I had some pictures of that as well. Oh, fuck, that's too many S's, maybe? Mars is. We're working on it, folks. All right. Why for no go? Okay, there we go. And here's what they look like. So this is Deimos. Viking flew by, and Mars Express has taken images. We can talk a little bit about the surface morphology if you're interested. They're not spherical, right? What kind of things do you see here? Craters, right? So similar to the moon, they're highly cratered. What's the major difference between this object and this object? They cone-like? Yeah, it's a little hard to tell, right? Because this is a Viking project picture and grainy resolution will hide imperfection. There's one very, very remarkable feature about Phobos. Nope. Giant crater, yeah, that's obviously a bad day for whoever was living there, right? It chonked and then another one hit inside of it, which I think is really cool. That's not the thing I'm looking at. Yeah, there are these lines all the way across it, right? And this is currently a subject of a lot of contentious debate. What we think is going on is we think that Phobos is going to break up. Not with Mars, but like it's going to just like be broken apart due to tidal forces. So it's the closer of the two moons, and we think that the pulling, differential pulling of gravity is slowly pulling this thing apart. Now you can begin to ask the question, where the fuck did they come from? Right? They're weird. They don't look like our moon, so that must mean they're strange, right? No, that's not fair, but you know, this is sort of like how we think about things as human beings. So the biggest question you want to ask is, did this and this form with this? Or was it captured later? So both of these objects orbit roughly in the same plane and roughly in the same direction. That gives a little bit of credit to the idea that they formed, that they formed with the object. Whether they were captured and regularized, you know, it's hard to say. Okay. We'll have some more stuff on that. Just a little bit more about these two bodies, just while I have you. Phobos is here, and Deimos is terror. These are the henchmen of the god of war, Ares, in ancient Greek mythology. So, of course, Mars, I mean, I don't really know how they went through this in a very strange way, right? Like Mars is the Roman god name, but they didn't want to give the Roman names for fear. They wanted to give the Greek names for fear. Make it make sense. Anyway. So they're very difficult to observe without photography. Weren't discovered in ancient times. They weren't known about. The only ones that we knew about during Galileo's time were, of course, the Venus Jupiter. So during 1877, we saw close approach to Earth and find how big these things are. I think we'll talk a little bit about close approaches in homework 4, but I don't think that we planned out what we're doing next. So I'd be fine. Hold on. So this is really strange. Do you know Gulliver's? Oh my God, I can't do this today. Gulliver's yes, Travels. You know this book? Okay, read it. It's really fun. It's the one where it's a giant dude and he gets like tied down by strings. No. All right. All right. So Jonathan Swift, Kepler loved numbers, and there are some people who are like really got a fixation for numbers, and this is this pseudoscience called numerology. So like the idea that like numbers somehow control different aspects of the physical world. And Kepler was like, he liked it. Trying to be very specific about my words here. I would use different words we have here. So he said that Earth had 1 and Jupiter had 4, so therefore Mars must have 2. He was right, but that's fucking weird. and of course Jupiter is wrong. Because Jupiter has like 70 or something, and Saturn has much more than 8, etc. But that's really interesting that you know the first time you talk about Mars's moons is in this context. Okay, I'm gonna yeah, I'm just gonna leave you with this, and we'll talk about it in a little bit later. So Eugene Antonaldi, these are observations. You know, when they had a telescope and they were finally looking at Mars, they started to like draw what they saw. And we can make this comparison now with modern telescopes, and I'll talk about this in more detail. But you'll notice some of the things that they drew on here. They couldn't see, they didn't have the Hubble Space Telescope. They were just looking through a fucking telescope. And they saw some of these like dark regions and light regions. And the reason why you have any idea that there are green men who live on Mars has everything to do with this type of observation, where they could swear that they saw canals, like places for folks to go from point A to point B by water. And they weren't that wrong. They were just naturally occurring as opposed to a civilization with connect. Alright, so I'll leave that thought up and we'll talk about this more in detail, on Thursday. Classes.